Okay, so welcome to the second lecture series in the theory of machine learning. We will try to finish this book as much as possible. That gives you a very solid foundation in machine learning, not just algorithm but also theoretical aspects of machine learning. So last time we looked into various ingredients when we try to learn from data, and here we discussed learner's input. So in this case, obviously learner is some algorithm, okay, or some software or something like that, and then you're supposed to put some input for the learner. Basically it's a training data, and then this training data means we have some features, and then we have the labels for those features. Okay, so sometimes we call it instance and so on. And we discussed something called measures of success. So once I develop a learning algorithm, then I want to know whether the algorithm is doing well. So basically we say that the algorithm does well when the error on the test data, the data where it has not seen during training, it does less error on the test data. Okay, so we have defined something called empirical risk or training error. Okay, so there are like different names for that, and yeah. So and then we discussed something. So what we defined is error of a classifier. So it's good to kind of recall this. Error of a classifier is denoted by I in M such that hxi not equal to yi and divided by M. So if we recall, this is now the probability. So basically for I in M means for how many samples, right? So total we had M samples, and then we are saying count all those samples for which your prediction was not correct. In other words, the hypothesis that you learn, the model that you have learned is not matching the actual level. Obviously we will have the test data on which we can compare this. So test data also has the labels, and then we divide by M. So basically number of samples on which I had bad predictions divided by the total number of samples. So that gives me the probability value on how many cases I have failed. Okay, so and this is obviously this error is defined on sample. Okay, so S stands for sample. So this is an empirical risk, okay, or training error, or training error, and yeah, so basically we have empirical risk because we define it on the samples itself, and sometimes we call it empirical error. Okay, so these are errors calculated on the samples. That's why they are called empirical or training and so on. Okay, but if we calculate this on the actual distribution, obviously we don't have the distribution in hand, but then in that case we will call it true error. Okay, just the risk. Okay, not the empirical risk, but just the risk. And then we saw something called overfitting. Overfitting, we have discussed this a lot. So in machine learning, what happens is you can have a very powerful model. Okay, and so we saw an example of a line fitting where we had some sample data and we tried to develop a model that fits this data. Okay, so in this case, let's say the possibilities I have is linear, okay, or I can have quadratic, okay, or I can have cubic, which will fit the data even more. So in this case, yeah, the models could be so the theta 1 x plus theta 0, so linear, okay, and then theta 2 x square plus theta 1 x plus theta 0, this quadratic, and then theta 3 x3 plus theta 2 x square plus theta 1 x plus theta 0, and so on. Okay, so these are the possibilities for the hypothesis H. Okay, and this is indeed parameterized by theta. Okay, so what we have seen is that when we are trying to learn pattern in the data, then we have to pick some of the hypothesis, and in this case it's like linear, it could be quadratic, it could be cubic, anything I can have in hand basically. Okay, the only thing is if your model size is, so as I grow with the degree, you can see the model size here is theta 0, theta 1. Okay, these are the parameters I need to estimate in my, so in this case I have two parameters to be estimated, so a little bit easier. If I go to higher model, then you have theta 0, theta 1, theta 2, and then if I go to cubic, then you have theta 0, theta 1, theta 2, theta 3. So obviously you can fit a data by using a very powerful model. By powerful I mean the model with larger number of parameters. Then you can do that certainly. Okay, but you may overfit. Okay, so that's the problem. Or in other words, we have also seen that in machine learning, overfitting also means, extreme amount of overfitting means memorization. Okay, so then you are essentially memorizing. Okay, so this is a thing, this is something you have to keep a check when developing machine learning model. And in fact, this is one of the biggest problem. Okay, when you are learning, you will do very well. There are many powerful machine learning networks. For instance, we will see at some point neural networks. So these neural networks are extremely powerful. We will see. So here we are looking into polynomials, right? But then in neural networks we have like multiple layers, and then parameterized by many theta, and then you have nonlinear activations, and so on. Okay, so such a model in practice can kind of fit a wide variety of data, but then again you have these similar problems that will it overfit at some point, which is something we want to avoid. So overfitting becomes a very important problem. It's related to generalization basically. So generalization means once I have learned a model, whether it will do well on the new unseen data. Okay, that's the whole idea of machine learning basically, because training data is already there. What is challenging is to predict on the new data. Okay, so overfitting happens when I have a very powerful model. Okay, by powerful I mean large model with large parameter has more capacity to learn basically. Okay, because there is more parameter. Okay, so then it can bend a lot. Okay, and it can fit the training data very well. Okay, but it can create problem. Okay, because it's fitting very well. Okay, sometimes data itself is not very perfect, so minor variations in the data should not be fitted completely. Okay, that's also, so ideally it could have been quadratic, but then you saw that this is not exactly fitting, and then you went for the cubic. Okay, so these are the things one may have. Data collection you usually have is not correct. Okay, or not perfect. So in that case again you have overfitting. So then ideally you should have maybe gone with this. Okay, because if it was quadratic, then it's very likely that the new test data was here, but you used a very powerful model and then you are predicting this now, which is incorrect. Okay, so these are the problems. So this will incur a lot of error in the test phase. So this is the main concepts we take from the previous class, and today we will go into very abstract concept. So we will use epsilon delta definition to prove learnability. So we will dive into theory. So we will say under which conditions we can guarantee that it converges. Okay, so one thing we take for sure from so far what we have developed, the intuitions we have developed, is one thing is problematic for sure, is that you should not allow a free hand on the hypothesis class. Okay, freehand on hypothesis class, you are going to screw up with overfitting, or in the worst case, memorization. Memorization extreme case we have seen where we had this case, okay, and you explicitly memorized what was inside, okay, and the uniformly distributed, and then when the new, so you explicitly memorized the data which were inside, okay, you explicitly memorized, and the problem was that when a data is here and when a new data is here, since it was not part of the memory of these guys, now it's a 50-50 game. Now it will say 50% inside, 50% outside, okay. So because otherwise case it always says 0. So basically the probability depends on 50-50 whether it's inside or outside, okay. So remember the way we define memorize this. So hxi is yi, right. So the way we define the hypothesis was hx is yi, okay. So this is the extreme case of memorization, right. So there exists I in M such that h xi is yi, or I mean x is xi, it's 0 otherwise. So this is where I am explicitly memorizing. I am saying that so during the training I am saying that, okay, what x you are giving me, if that x happens to be one of the training data for which the labels has been given to me, okay, then in that case I am going to give the label yi, and this will memorize for both inside and outside, obviously. So yi could be inside the square or outside the square. So if xi is this, then obviously the label of this is 1 during the training data, so it will give yi. So let us say I put this guy x here and it looks into the training data. Oh, okay, this x is part of the training data and it was given a label 1, which means inside the square, memorized. So then this is also part of the training data. It goes here, it checks whether it's found in the training sample. Yes, training data is there, and for which the corresponding label is yi. In this case yi will be 0 because it's outside the square. So for all this, let us say these are our training data. So for all this it memorized, right. Now the new test data comes, then it will check here, right. So it will check whether it's part of the training sample. X is sum of the xi. No, not really, because this is a new thing now. So this is not part of the training data, hence it's not going to give this. It will go to this case. It is 0 either here or here. It was 0 in both cases because it's not part of the training data. So it's saying this is also 0, this is also 0. So in like 50% of the cases is going to be wrong. Half of the cases are going to be inside because let's say some random point. So now it's saying 50% here because it's not part of the training data. So now it's a probability thing, okay, because the area of this is half of that, then it's 50% error it's going to make. So this is extreme case of memorization. This is also a kind of memorization, but and it can be extreme by increasing the model size, okay. And this was a very, like, explicitly I took the points and then I said just memorize that. I mean you may do something like that, but the point is here with the models also you can end up memorizing, okay. So a very good intuition that we get from here, especially this example, okay, maybe not here because this was extreme case of memorizing, but from here what I learned is one thing is sure, I should not allow free hand on these hypothesis classes. That will surely going to, I mean surely, like almost surely going to screw up our learning generalization ability, okay. Generalization is the main thing in machine learning anyway, right. So certainly it's going to screw up. So a learning through, if we want to build a learning theory framework from here, one thing is for sure, restrict your hypothesis class. So if my hypothesis class is H, okay, then the hypothesis class size should be much less. So if I tell you, if I give you a possibility that you take a class of all polynomials, that's infinite, because polynomials can go up to infinite size, right? 1 degree, 2 degree, 3 degree, 4 degree, and essentially it may still be countable or something like that, but then it goes up to infinity, and that's where you will lose the there is a danger that you will lose the generalization ability. So one thing you should make sure for a proper learning is restrict your class of functions that you are going to fit, okay. So that you will see will be part of the theorem where finiteness of the hypothesis class is essential, okay. So a general question that we asked also in the last class is a fundamental question of machine learning is over which hypothesis class, okay, ERMH will not overfit, okay. So empirical risk minimization is essentially the training process, right? So if you recall, ERM is called RM. So the name maybe, yeah, a little bit looks a bit strange, but empirical risk minimization is essentially you are trying to fit a model for the given data, and this will be done over some hypothesis class H, okay. So then for learnability, a fundamental question now is over which hypothesis class ERMH learning will not overfit. Okay, so yeah, I mean, one intuition is here. I need finiteness on the size of the set. So let us see that. So finite hypothesis classes. So a simple restriction that we have seen is impose bound on the size, impose bound on the size of our hypothesis class H. So one of the conclusions we can make, if and we will also prove today, so if H is a finite class, implies ERMH will not overfit. Although you see, I'm not saying that it will not underfit, okay. So what I'm saying is like it will not overfit. So it may happen that you restrict your class so much that, let's say it was supposed to be fitted by a cubic, but then you restricted your class up to quadratic, okay. So in that case it may underfit also, okay. So at least for the moment we are proving upper bound, okay. So today's class we will prove a major theorem, a basic theorem on when we can ensure that learning will happen, okay. So we will prove a main result, and then we will relax that theorem step by step and try to prove in a more general sense, okay. So first let us try to prove this with some assumptions initially, and then we will relax those assumptions, okay. So we'll start with a little bit easier case and then relax, and then we go to VC dimensions also at some point. Okay. So the first thing we will assume is something called realizability assumptions. So I will first write down and then explain. So realizability assumption tells us that there exists H star H star, that's a small H star in the hypothesis class H. The hypothesis class is the set of all hypotheses or the functions that we are going to use, such that, so there exists H star in H such that LDF of H star is 0. So LDF, if you recall, LSH is defined over the samples because these samples are known, xi, yi are known, and so on. But in what we really want is this error, LDF. LDF is the true distribution, okay? And we want our hypothesis to give me 0 error while I'm working with the test data, okay? For which it has not trained for, okay? So ideally we want this true error, right? Or it's just called risk, okay? Or sometimes called test error. So what we are assuming here is that there exists H star in H such that the true error does go to 0, okay? So there is an existence of H star in H such that this happens. Obviously these are defined in probability terms, so when we say 0, then we are saying with probability 1, okay? Okay. So that's it. This is the realizability assumptions. There is existence of H star. So it may happen that in the hypothesis class I am choosing, there will be no possibility of ever minimizing the test error because I choose a very different class, okay? So it may happen that the set of classes of functions I wanted to fit, they were completely off. They could never fit because the class of functions itself was not a correct one, okay? So in this case we get rid of that. So one of the things we want to know is whether realizability assumptions also prove that LS H star is 0, okay? So does it guarantee that, right? LS H star will be 0 or yeah, so that's something we want to know, right? If it's error 0 on the test data, then what about on the samples, right? So can we say this for sure, right? Samples are coming from D itself, right? Samples are coming from D itself. So I have said something very strong already on the distribution itself. H star is supposed to give me 0 error. Samples are a subset of that. So samples are also taken from D, the underlying distribution that we don't know. That's another story. But this is hypothetical that, okay, if there is H star which indeed knows the data, it can make the 0 error. But then I am saying these samples were also collected from those. Of course I didn't knew that, but then if there is existence of H star, it must be making the empirical error also 0. Okay, so and not just that, but also the hypothesis class that I learn from the sample itself. So let us say HS, it will also make this 0, okay? Because what is HS, right? So let me recall the definition exactly. Yeah, so HS is argmin H in the hypothesis class and LSH. So HS is essentially the hypothesis that minimizes the empirical error, because the LS is the empirical error and H is taken from H, for which it minimizes the empirical error. But shouldn't it also, that same S should minimize, make it 0, right? I mean, shouldn't HS also minimize the, I mean, that's the definition, right? Because what is happening here, right? Like, let us try to see, do you really get this, right? And does realizability assumption imply this? So does realizability assumption imply also this? So what do you think? Like, I claim that it does imply that also. Okay, but why? Look, I gave you the whole of this, right? Whole of this H is there, right? In the worst case, you could have picked this. And that is true for all, including the samples. The fact that Hs could be something else also from H star, but the thing is that H does include this H star, which is globally making the error 0. So in the worst case, Hs I can always find to be H star. That will certainly make this LS 0 empirical, because empirical is just one sample of the distribution D. Okay. So so another way to say is that you can have some other Hs which is different from H star also, which can still make it 0, but in the worst case, okay, in the worst case, you always have H star in hand, right? In the worst case, H star is there in hand. You get that? Yeah.
And the second step you wrote, ls of H star equals 0. It's not possible, right?
Why?
Suppose you pick a singleton set. And so basically to make the probability 0, S star of x must be equal to f of x. And we can do it for every x in the set. Basically we are saying that S star is same as f. But the earlier condition or loss over d comma f equal to 0 doesn't imply that, right? At some points the functions can differ, but the probability of that will be very small that it won't affect the overall. So like the function need not be equal to make the probability of difference to be 0.
So you're saying this may not be true, right?
If this is true, it implies H star equal to f. But from earlier condition, it's not true.
Which earlier condition?
LDF H star equal to 0. It's a probability measure of
Yeah.
how different they are.
Yeah.
They can be different at one point in a continuous space and still it would be 0.
But whether it's continuous or not, I mean, we know some way to compute probability, right?
No,
I'm not going into that. I will compute the true, I mean, correct way, right?
No,
If it's
it equals to 0 doesn't imply H star equal to f exactly. It can differ at some selected points, right?
It may, yeah, it may. Okay.
But the
Yeah, I
limit
get.
condition rigidly defines that H star has to be equal to f. What I'm trying to say is below condition is a stronger variant above.
This one.
Yeah, above.
Above.
Yeah, this is a stronger variant. It's exactly equal to.
No, all this is in probability, with probability 1, with probability 1.
Yeah, but I'm picking, suppose S to be singleton set only.
Okay.
Then S star of that value must be equal to f of x, right? To make the probability 0.
Mm-hmm.
And I can do it for every single element.
Mm-hmm.
So it implies H star is same as f. But the format doesn't imply that.
Mm-hmm. You mean this implies this, right?
Yeah, it doesn't imply that.
This doesn't imply that.
Yeah.
What about this?
I mean, if you assume the second, it implies the third, obviously.
Yeah. Yeah, maybe I didn't get your argument very well, but let me explain what I understand from here. Yeah, let me explain. Yeah, let's see. So let us see this first. This is fine.
Yes.
This is fine, right? Okay, so let us like. So realizability assumption means that there is an H star in H hypothesis class, and for which on the true distribution, which is test error, test data, it will give me 0 error. Okay, so that's like the true error is 0, and HS is a hypothesis that I learn by looking at the training data. That's why it's S sample. Okay, and I find an H in the hypothesis class for which the training error is 0. So what we conclude from here to here at least is the realizability assumption must ensure that LS HS is 0, right? So that's like understood, and it is going to be 0 because HS is coming from the hypothesis class, and in the worst case, I can always pick an H star, HS to be H star, which I am allowed, for which I will make it 0. Okay, that's the lower bound I can get. I cannot go lower than that. Okay. So realizability assumption does imply this, right? So realizability assumption does imply LS HS 0. Okay. That we need in the proof. Here we have some argument here that I may not have understood. Like, okay, so let's see. Yeah, that's exactly what I said, right? So I always have a possibility to choose S star because it is in H. H star is there in H. So samples being a subset of the distribution, it can give me 0.
Yeah, it can give you for some S, but say for every S, it has to give 0.
Okay, so the question is like, for does it happen for every S? If I fix an S, then it's okay, right?
So basically, former doesn't imply the distribution has to be exactly the same, right?
Yeah, distribution has to be same, exactly.
No, H star and F can differ at some points, right? Like suppose you have.
No, once I have, yeah, these samples are coming from this distribution. So, yeah, so that we don't change, right?
No, suppose like D is R.
Yeah.
And F is suppose a normal distribution,
Hmm.
and S star is a normal, except at 0 it is 100.
Mm-hmm.
So in this still case, the loss will be 0, right?
Mm-hmm.
But the probability L of singletons at 0 would be 1. It won't be 0.
So D is
Normal, real.
real.
Yeah.
No, it should be distribution, right?
Yeah.
Some distribution. Okay.
Okay.
Some distribution, underlying distribution, some
0 to 1 normal.
normal. Okay, let us say normal. Yeah, whatever. Yeah, normal. Okay. Then
You can pick F to be like constant 1 over all R.
F to be constant C
Yeah.
for all. So Fx is C for all x in the domain X, the feature set. Yes, and then
H can differ at 1 point.
H differs at 1 point. So this is the H you learned, right?
So basically, I'm artificially dividing Hx equals to C for all values except 2.
Hx is C. Okay, let's see. So the model that you learn in Hx equals T.
For all point except 1 point. Say 2 be 2.
So for all
X not equal to 2.
x not equal to 2, and this is
Anything.
anything else 0.
For x equal to 2.
So here let us say C is not 0, and then for x equals to 2,
Yeah,
right?
now LDF this H is 0. Really. They are the same distribution. It's just different at 1 point. And
So LDF, right? LDF H
it's 0 here.
is 0 here.
Yeah. But L of singletons at 2, H star is not 0.
Okay, and then
L of singletons at 2, S equal to singletons at 2.
we have to put H, right?
Yeah, I'm defining S first.
You're defining H.
S, sample space.
Sorry, sample space is
Single set 2.
2. Okay.
Empirical is over this S star in
Okay.
this sample space is 1.
So for the H,
It's 1.
it's 1. So sample space is 2, and for sample set contains the number 2, and for that the prediction is 0, right? So prediction is 0, so that means it's making 0. I mean, so sample space has just 1 point, right? So m in this case is 1. So the empirical error that we have is 1 only in the sample space, and then for that xi for us is 2, and is hxi not equal to yi? It's not correct, because the way we define h is like h of 2 is 0. Okay, so it does match. We need to define the training data also, right? This is our hypothesis, right? And what about the training data? Like, so sample contains 2, that's I know. And then the corresponding level is C. So 2, this one. So this is our training data. So for a given x, I predict C. Okay. So this is the training data, only 2, and then the training data must have level, right? So obviously, so this is 2 is predicted to be C, and the hypothesis that we learn is defined to be, if it's 2, then it's 0. So basically, it fails, right? So okay, whatever. So we learned something. Basically, it fails already, but then we calculate the empirical risk. So in this case, a set of all I in M, so in this case 1, and H of 2, wherever it's not equal. So in this case, indeed, at one place it's not equal, because H of 2 is 0. So it does, let's see, it's not corresponding to the sample, that's what I'm saying. At 2 it's predicting 0, but it should have been C, so it's not equal, right? So then the count of the samples over which my hypothesis is failing is 1, okay, because H of 2 is 0, but the training data is saying that it should have been C. So this is like 1 over M. So M is 1 here, okay? M is 1, so this is 1, okay? So LSH, what was predicted is correct. Indeed, LS is 1, so this is fine. And if we look for the H star, right? H star in this case will be the other one. So let us also write the H star. So in this, for this problem, okay, this problem setup, do we have, can we create H star? So yes, we can create H star, but this will be like in the opposite of that. So H star must be the one that does learn perfectly, right? So
this H is an H star, because the loss function over the entire distribution 0.
This H itself is
H star.
is it right?
Yeah.
This H, 1 second, huh? But how come the training itself is, so this H star should be such that on the distribution it's 0, right?
Yeah. The distribution being continuous, it can be off at some certain selected points, but over sample space, because it's for all sample space, we can like pinpoint like every single allocation very different.
But then like we have to show, we are taking normal, right? And we have just one.
It's a very artificial example, but
Yeah.
point stands. The first condition doesn't apply the second.
So how do we interpret this? LDF H star is 0, right? That's what I want to conclude here. So for this H, we are claiming that this H is H star. So this is like at point value it's 0, and then it's constant, something like that. So we are claiming this to be our H star, and we are saying that LDF of that will be 0, okay? So the only thing that I'm want to make sure, like so far the claims are okay. Only thing I want to make sure now is for this H itself, is this 0, right? So LDF definition, right? Let us write down LDF. It was defined in the beginning. So this is by definition probability that X such that Hx not equal to Fx. Okay, or the other way to say is that I sample from the distribution D, and then for these Hx is not equal to Fx. Okay, so we want to ensure that for this choice of H, which is very special here, this LDF is supposed to be 0.
The difference is 1.2. So basically, takes the value exactly 2,
Hmm.
which is 0 obviously.
Interesting. So yeah, I mean here training data is just one. So obviously I know fx only for one of them, and if x comes from anything else, that's something underlying I don't even know. So if x is 2, the problem in this case is it goes a little bit, it's because I don't have any test data also to kind of verify here. It's just one thing in the training data on which we have calculated everything, and then when I'm looking at f, then this f is again defined only for this one training data, right? But okay, let's see. So for any other point, the way we define h to be, yeah, let's see. So for any other point, so if x equals to 2, indeed I'm failing. That's fine. Okay, that's there. So fx should be c. For h equals to 2, for h equals to 2, I'm defining it to be 0, but f of 2 was c. So certainly at 2 it's failing, but at any other point, how do I know f?
F is given, right? It's C for all x. So like we are given the distribution, we are given the label of every single point in the domain of the distribution.
But f,
And we predict
yeah, fx is c, sorry. Yeah, you have already pointed out, right. You have already pointed out f, okay. Now I wonder how did you quickly cook up so many things at a time. Okay, that's nice. So, okay, so f is c is given, okay, and so one point they differ, which is at x equals to 2, okay. So let us like decode this step by step. X equals to 2, certainly at one point they differ because h of 2 is not f of 2. Yeah, I mean this is constant anyway, right? So one point they differ, and that other points they match basically, right? Agree, so they match. Okay, now it becomes kind of interesting because if I mean which kind of measure I'm going to use, right? So if I do scale divergence something, scale divergence kind of thing, probability measures, right? How do I, so at one point they don't match.
we define it as just the collection of the points, right?
It's like I have one of these, and I have one of these where they don't match. Okay, so basically I have a vector y. Okay, some values they match. Here they don't match. Okay, and this guy is also like same everywhere. Okay, so basically at this point they don't match. Okay, so now it's like how do I compare them, right? They don't match at one point.
We just gave that previously, right? Just consider the probability of x for which it differs, right?
Hmm.
It's just a p of x, where x is a set of the point where they differ.
Hmm.
So like we don't need to go into clear divergence or anywhere.
Hmm. Yeah, I mean,
This is probability x takes sample from 2, x takes the value of 2, which is obviously
if it is a discrete case, then I take the ratio.
In discrete case, like
Always take the ratio, right?
yeah.
In that case, it's valid. I agree.
In discrete is always valid.
In discrete, yeah. So let us assume, and so all this makes sense, okay? In discrete, I have like finitely many samples. So then probability will be a number of places where they don't match divided by the total number of places. The number of places they don't match is 1, and but discrete and
It's still like it's hard to cope up with. Like it feels like it would be true in that case.
I mean, it will be, if it is finite, then it will be 1 by something, right?
No, it depends on the PMF, right?
Yeah, it depends on the PMF, right?
How much PMF. And
Yeah.
it will be finite. All this is great. It won't be 0.
Yeah.
If it's 0, it's all good. But if it's not 0, then
Hmm. Yeah. That's right. So what we learn from here is it may remain close to 0, but may not be 0. That's what it seems to be. Okay. In this very special case, So it can be kind of 1 by n, let us say, and as this tends to 0 as n tends to infinity. So making yeah, so this may not be exactly 0, okay, but maybe close to 0, okay, or asymptotically it may be 0 but not necessarily equal to 0. That's what we learned from here, right? But this is okay, right?
I use second to imply third. I don't know how to go first.
From here to here.
I don't know how to go directly there. Can you repeat that?
Yeah, so what we are saying is that hypothesis class H, I always have H star for which the whole error on the whole distribution is 0. Then what I'm saying is that if I compute the empirical risk, okay, then the HS that I find after training over the sample, and this is the argument, but then I'm given a free hand, H is from H, then I'm necessarily going to have LS HS is 0. And the argument is that this H could have been H star also, and this H star is giving me 0 throughout, including the samples, which comes from D. Samples are just part of, assuming that the sampling has been done with the D distribution itself, so the samples are also part of the distribution. So H star is already there. In the worst case, I can put H star, I can use H star, which will, if this holds, then I can have an H star, and all this is with probability. Okay, when we are writing equalities, no, all are with probability. At 1 or 2 points, they are allowed to be off. Okay, in that sense, even this will make sense. At one point, it could be off. Okay, so maybe we have to be a little bit precise when you're talking. You say with probability 1, it is 0. With probability 1, it is 0. Then it allows these kind of arguments, one-off thing. Okay, it was a good discussion. Okay, that we should be a little bit careful when you're saying equal to 0. Okay, because all are with probability. Then these boundary cases are handled somehow. Okay, so okay, so in the initial part of the learning theory, what we are assuming is that there will exist a model from the set of assumed hypothesis class which will make the true error or the test error 0. That's an assumption. So as I explained here, fitting a data with a curve, then you are assuming some hypothesis class, then there must be some polynomial degree for which it will fit the training data as well as the test data. So this is a very strong assumption in some sense. It's saying like perfect, okay, perfect model, no error, test error, no training error, perfect. Okay, I mean with probability 1. Okay, so we have to be a little bit careful. Okay. So this is the first of the assumptions, and then we will also put a restriction on the size of the hypothesis class, and we saw the reasons why. Okay, essentially it can overfit. Okay, so this is called realizability assumptions, and okay, so we have some IID assumptions, and if you recall a little bit, like we don't have to know just the definition of IID, that would be good enough. This independent and identically distributed. Okay, so we have done the realizability assumptions. So all this is okay with probability 1. Okay, we have to be a little careful with probability 1, with probability 1. Okay, so some couple of points difference is allowed. Okay, okay. So indeed this is guaranteed, but what we really want is that this HS actually makes error close to 0 on the distribution itself. Okay, so what we want LDF HS is 0, right? That's or we are interested in, let's say, okay, we are interested in, I mean ideally it should be 0, right, but we are interested in this. So obviously it depends on the distribution and the samples basically, okay. So what kind of samples you pick, right, that has a role obviously, and what kind of distributions, underlying distribution it is, right. So these will play a role when we try to prove learnability, right. So for an algorithm, that has access to the sample S, okay, it should depend on the relationship between D and S, on the relationship between D and S. D is the distribution, S the sample. That makes sense. Like if I choose a bad sample, no matter what I do, it's not going to work, okay. So the sample S may not be representative enough of the distribution itself, okay. So there are many things that depends on the sample itself. So a common assumption in the statistical learning community is that S is IID, okay. So the samples are generated, training samples are generated independently of each other. So common assumptions is that training samples are generated independently of each other. So this is why, these are motivations for why we use IID, independently of each other, right. So that's why there is a one paragraph on IID assumptions, right. So some remarks on IID. So IID here means independent and identically distributed. So independent in the sense that the samples that we are generating, they are independent random variables, okay. So independent is like, so there is a way to define independence. So basically the random variables, the samples are independent, meaning the probability, joint probability, if you recall, is product of the individual x and probability y equals to y, okay. So these are like the marginal. So that's how we define independence, we have seen also before. And identically means that all are coming from the same distribution, okay. Both x and y, both x, y come from same distribution. Coming from same distribution doesn't mean they are equal, okay. They are sample, but the samples are different, right. So all this means that every xi in S is freshly sampled according to D, the distribution D, and labeled by f, the label function. And we denote this assumption by this fact by saying that S sample from Dm. So this notation says that since a sample has m instances, I did a Cartesian product of that, saying that each instance is coming from one of the D. The sample has m of them. The first one came from D, second one came from D, and so on. So this is just a notation, okay. So each of them come from D, and there are m of them. So where m is the size of M is the size of S, and dm denotes the probability of m tuples, probability of m tuples induced by applying D, induced by applying D to pick each element, of the tuple independently of each other, and so on, right? So obviously sample S is a window for the learner to have a look into the underlying distribution. Sample is what a learner has all the time, and that's your only window to make some estimate on D. So obviously larger the sample gets, more better view of the underlying distribution you will have. So there will be one of these assumptions also, that you should ensure enough samples in your learning model, okay, so that it learns well. So the first assumption is bound on the hypothesis class size. Second will be sufficient number of samples, and obviously like those should be representative of the, so more diverse it is, the better it will show you the distributions in a more better way, right? So larger the sample gets, more likely, so larger the sample, more likely it is to reflect the distribution D. So HS that we have, the hypothesis that we build after looking at the sample, has to be a random variable, okay? So we should keep that in mind, so we should like write it down. So since LDF HS depends on the training set S, and the training set at S is a random process, okay? So HS is comes from training set, which is a random process, so HS should be a random variable, okay? So depends on the training set S, which is generated by a random process, which is picked by a random process there is randomness in the choice of the predictor HS. Hence this justifies that HS is going to be for us some random variable over which we can apply all the whatever, like as a normal random variable, whatever we do with random variable, we can do it with HS. So as I said, there is no guarantee that S will always give you a good HS, right? So no guarantee that S will give good HS. It's obvious, right? And if sample size is bad, HS is going to be bad, okay? So if you look into the papaya example, so like if you remember, we started with those examples in the beginning. So we go to the island, and then there are like papayas and so on, right? So many entries are there, and then what if you happen to like go to this island, and then somehow you only tested like 2-3 papayas, and those papayas happen to be tasty, and all those papaya that you tested, some of them, sample of them, they happen to be tasty, and that you take it as a sample, that's incorrect, right? You did not had a sample where the papaya were not tasty, right? So these are the extreme cases that can happen in the sample. So let us like go quickly to prove this result. Yeah. So let us define few things like the another set of problems that we that we are coming into, right? So one was the probability, I mean the hypothesis class size, okay, we handle that. Then we had this realizability assumption. So whether the class of hypothesis we are choosing will one of these will certainly um, is present in my hypothesis class such that it will fit and so on, right? So that was the realizability adjustment. And third set of ingredients that I need are on the samples itself. Okay, so what is your confidence on the samples? So we need to characterize that. Okay, so we are trying to go in that direction now. So let us say if delta is the probability of getting non-repetitive, non-representative samples. So we are kind of characterizing the sample quality itself now, and all this will go into theorem. Okay, so non-representative means like samples that were really not useful, okay, from training point of view. So if delta is the probability of getting non-representative samples, then okay, and then okay, so let us define like 1 minus delta to be the confidence parameter. Okay, then call 1 minus delta to be the confidence parameter, confidence when you do this some of these like hypothesis testing in statistical estimation theory, then they have these kind of things. Okay, confidence parameter, confidence interval, but we don't have to know these things. For our purpose is fine. So if delta is the probability of getting non-representative sample, then how much confidence I will have will be 1 minus delta. So that's fine. So okay, so this is the confidence parameter of our prediction. Also, so this is one of these, and another is we cannot guarantee a perfect level prediction. Okay, so we characterize that by some epsilon. Okay, so we are accurate up to epsilon. Okay, so we cannot guarantee, can't guarantee perfect level prediction. So we introduce another parameter okay, which is called, let's say, accuracy parameter. And it's yeah, which is denoted by epsilon, and we can interpret this like this: LDF HS, okay, is greater than epsilon as a failure of the learner. So you put some epsilon as your parameter threshold up to which you will be happy with the prediction of HS, okay, HS that you learn from your data. So you put that, and then you say, if I'm making an error which is greater than my threshold epsilon, I say that my model failed basically. Okay, and if it is less than or equal to, we say you are happy. Okay, so determined by this. So if this is greater than, you define it to be as a failure. Obviously this is your choice. Okay, as a failure and failure of the learner. While the other way, when it's less than or equal to epsilon, we say that it's approximately correct predictor. Okay, and then later we will go into even other definition of PAC learnings, probably approximately correct. Okay, but for the moment we say approximately correct. Okay, so while this is defined as or viewed as approximately correct, Okay. So this is a threshold epsilon, usually depends on you how much threshold. So if it's less than equal to the HS that you learned from your samples, now it's making test error very less than the threshold that you said. You are happy, you say it's approximately correct. So essentially we are interested in upper bounding the probability where I'm going to fail, right? So LS is defined to be the probability where I'm making errors. So basically we need to upper bound that. So after fixing, obviously we fix the level functions, fixing f, which is the labeling function. We are interested in upper bound. Okay, we are interested in upper bounding the probability to sample m tuples of instances that will lead to failure or success, depends which one you want to, which way you want to see, that will lead to failure of learner. Okay. Now let us define a notation which is S. So and then when I write this, then it's restricted only to features, okay, without labels. So this is a sample, but then restricted only to the features. So this denotes only collect the features, not the y labels, but only the features. So there are m of those. So what we want to upper bound is this quantity, the probability of these so samples restricted to x on which the true error LDF of HS is greater than epsilon. So we want to bound this. To bound this, it's important that we have also some handle on samples which are kind of non-representative or like the bad samples. Okay. So let us define a set HB which are kind of bad, and these samples are bad because, and there could be also misleading ones which do very well on the training, but then they fail miserably on the test. Okay. So so let us characterize those samples as a separate set. Okay. So let H be, so B, maybe you can say it's bad. Okay. B stands for the bad. Be the set of bad hypothesis I mean not the sample, I would say, maybe I said sample, it's I mean HB, which is the hypothesis class, set of hypotheses. Okay. That is, so HB is defined to be set of all H coming from H such that LDF of H is greater than epsilon. Okay. So you collect all those hypotheses from your hypothesis class that are going to necessarily make error larger than epsilon. So these are we collect it as a separate set. In addition, let us define a set M which is S X such that there exists H. So these are now misleading samples. M stands for misleading samples. So you can have set of hypothesis class which are not good ones, and then you can characterize the samples which are not good ones. Okay. So collect all those samples for which there exists H in from the bad hypothesis class for which the loss is 0. Okay, so these are the misleading samples. LSH is 0. Okay, so what we have done, we have collected all those bad hypotheses in HB, and if for those bad guys there are samples on which it is giving me the empirical error or loss 0, then those samples are also misleading ones. Okay, so because they will not generalize those. So okay, so that's how we characterize these. So this is called be the set of misleading samples. So in words, what does this mean? This means that for every, I mean, it's the same thing what I wrote, I've written, but just for a little bit more clarity. So for every sample in M, there is a bad hypothesis H in HB that looks good, hypothesis on SX. Okay, now let us look into, so what are the ingredients we are, so we are trying to prove a first result on a guarantee of learning. Okay, now guarantee of learning depends on many things, like we have seen: samples, representative samples, hypothesis class. Okay, so we are more or less all set to prove this result, but having this realizability assumptions, what are the consequences how on these H, B and M. Okay, so let us see some remarks on those. So realizability assumptions, so realizability assumption implies that, so we have seen that it implies that LSHS is 0, okay, with probability 1. So what does this imply, right? So this implies that it follows that, so reality this, then it follows that the event which is LDFHS greater than epsilon can only happen if for some H in HB, the bad hypothesis class, we have LSH is 0. Okay, so I hope we get this. So the fact that you will make an error epsilon can only happen if for some H in HB, the bad hypothesis class, we have LSH equals to 0, because by nature bad hypothesis class captures all those where you are making epsilon error. Okay, so all are captured already here, so nothing is left out, right? So if in case you made this, then this must be the bad hypothesis guy, right? So it can only happen if for some this we had LSH is 0, because we are picking LS as an argmin something, right? So on the training data, I'm looking for H in my whole hypothesis class. Okay, so HS is argmin of H in H of LS H. So given a sample, given a data, I'm looking at the empirical error. I'm given a hypothesis class. By mistake, I can pick this HB, which is one of these bad hypothesis class, and it can give me this, because during training it did minimize this LS, it did minimize, but I know that on a true test data it is supposed to make an error. Okay, so that seems valid. By nature, by construction, we created bad hypothesis class already, so we know that this is going to happen. Okay, and this is also tied to this, and this can happen when we had misleading samples also, right? So, and this can happen, so this event will only happen if our sample is in the set of misleading samples. Misleading samples M. All these are tied, right? So there is absolute clarity here. Misleadings are the one that give rise to bad hypothesis class, so they are all connected. So formally what we have shown is this. So formally, in terms of sets, what we have shown is that Sx LDF of Hs greater than epsilon is in there should be inside the misleading samples. So whenever this is greater than epsilon, then that must have come from misleading samples. So it must be part of a subset of the set of all misleading samples. So we can write M as M is union of H in HB such that S restricted to X LSH is 0. Okay. Again, I have captured everything here because now I am taking union over the bad hypothesis class, and these are exactly those over which I am making a training error to be 0, but I know they are the bad hypothesis class. So all this collection of samples for which I am making a training error 0 with the choice of H from bad hypothesis class must give me all the misleading samples. So this is essentially a notation basically which is also like equivalent to this, so it's fine. This is just another way. We are supposed to use union bound and so on, so that's why we are writing this in a union form. Hence dm of Sx LDF Hs greater than epsilon is less than equal to dm m, which is equal to dm union H in HB S restricted to S and then LSH equals to 0. Okay, let us see this. So why is this less than equal to here? It's a subset, exactly. It comes from this star. A subset B, then probability of A less than equal to probability of B. Okay. Okay, and you can see that we are supposed to kind of prove some bound on this, because this is what we kind of have to put an upper bound on. Okay, what is the probability that I will make error greater than epsilon, okay, after learning HS. Okay, so essentially we are supposed to bound that, and hence we will use a union bound from probability. So next we upper bound the right hand side of this guy. So let us say this is our equation 1. So we upper bound that. Okay, so we upper bound RHS of 1 using union bound. Okay, so let us recall union bound. So for any two sets and distribution D, we have D of A union B less than equal to D of A plus D of B. D here means P, okay, probability. So probability of A union B is less than equal to probability of A plus probability of B. The union bound is also a general one. If you have more unions also, there is a general version of that, but we are okay with this case. So we will do that. So in fact we will need that exactly, right? It's like union of many of these, right? So union of basically right hand side of the one we have to upper bound. So probability of the union, okay, is less than equal to probability of those sets, right? So applying the union bound on right hand side of 1, what we get is the dm of Sx LDF of Hs greater than epsilon is less than equal to, so basically the so basically this quantity, which is this quantity, and this will be less than equal to sum of the probabilities, right? So this is less than equal to sum of the H in HB dm and Sx LSH 0, right? So this is just a application of the union bound. Now we would be interested in bounding each of the summands, right? So these guys, can we have some bound on these interior terms? So let us bound each summand of RHS. Okay, let us do this for and this is sum over all the bad hypotheses, right? So and this is sum over the H coming from bad hypothesis. So basically each summand is for one fixed H. So if I'm looking for one summand, then it's for one fixed H. So let us fix an H and focus on the summand here. So fix some bad hypothesis H in HB. The event LSH equal to 0 is equivalent to for all I, H of xi is equal to f xi. Okay, so we transform that ls h equals to 0, we now replace this by hxi is fi. Okay, so in the and also another thing we note is that the examples in the training set are all IID. So so they will be the joint will be product of the marginal here. Okay, so in that case we will get a product also. So let us see it here. So since the set are IID, then this implies dm of Sx LSH equals to 0, which is equal to dm Sx such that for all I h xi is fxi. So that's what we said previously. So we just replace LSH equals 0 by for all I hxi is fxi, and then use that this is IID. Due to IID, the product m of these joint probabilities will be product of the of individual probabilities. So this is d of xi such that hxi is equal to fxi, I equal 1 to m. So we used IID here, that simplifies a little bit. So now we focus on each of these individual terms here. What is this probability, right? So for each individual sampling of an element of the training set, we get d of xi such that hxi is yi is 1 minus LDF of h. Why is that? D of xi, so probability of that is 1 minus LDF of h. What was the LDF of h? It already characterized those where it was not equal, right? So it's like whole sample space is covered. This is the case where it's equal, and in the LDF definition it's not equal. So together they must be 1, right? So it should be the complement. So this is 1 minus that, right? So probability of this 1 minus of this. This is all where it was not equal. Okay, so that's fine. So 1 minus LDF h, and these are bad hypothesis class. So LDF h was necessarily greater than epsilon. Minus is less than equal to minus is less than epsilon. So since they are all coming from the bad hypothesis class, so because h is bad hypothesis class, so necessarily LDF, the generalization error, was greater than epsilon. So negative of that is less than equal to epsilon. So whole thing is less than equal to 1 minus. I need upper bound, right? LDF is greater than epsilon, so negative LDF is less than minus epsilon. Okay, so since LDF h is greater than epsilon, okay, this implies minus LDF h is less than minus epsilon. So essentially this is the fact we just recall. So this implies that this is less than 1 minus epsilon. 1 minus epsilon, that's it. So we have gone into the individual summands, but then there are m of these. Okay, so we have just bounded this guy, and there are m of these. So there will be 1 minus epsilon to the m. Now this whole guy will be less than equal to 1 minus epsilon to the m, and we can approximate it further. So let us do that. Okay, so now, so this implies, and 1 minus epsilon is less than equal to e to the minus epsilon. Okay, so this is a inequality result. You can try to prove if you want. So 1 minus epsilon is always less than equal to e to the minus epsilon. So this implies for all h in the bad hypothesis class, we have dm of s restricted to x lsh is equal to 0 is less than equal to, so here I am, right, and I did a bound on each of the sum n. This was less than equal to e minus epsilon. Now there are product m of them, so it will be e to the minus m epsilon. Okay, so this is less than equal to 1 minus e to the m, which is less than equal to e to the minus epsilon m, right. So where we are now, right, we can go back to this LSH thing. Okay, so eventually this was this, and then we came here, we bounded this, and so on. Yeah, so we already have this basically, and then yeah, so we recall what we have kind of like rubbed it. So recall the bound that we started with was S x L D F H S greater than epsilon, and this we had using union bound was this T M S x and then L S H equals to 0, and then we continued with this, and then we arrived at that, right. So and then for this we have already, we arrived up until here, and this is what we started with. Okay, this is what we started with. So essentially this is now upper bounded by e to the minus m. Okay, so this is, and this sum was over h in HB. Okay, so this sum was over h in HB, right. This is something we have written before, and what we have bounded, and this sum is outer one, right. So what we have bounded is this guy e to the minus epsilon m. This guy is e to the minus epsilon n, less than equal to that, and we are summing this over HB. Okay, so hence it will be size of HB times e to the minus epsilon m. Okay, that's our final bound. Okay, and that is how size also plays a role. Okay, if you increase, if you allow, yeah, in general hypothesis class to be very big, it's potentially including lot of bad hypotheses, and once it includes bad hypothesis, your chances of becoming this, because your upper bound is like you are relaxing it, so it can kind of start making bigger error and so on. So that's how it's okay. So yeah, so this is the result we have, where we see that there is a bound that includes epsilon, and then sample size m, and then also HB, and here this is a bound on the hypothesis class HB. So from here we can see that if the sample size grows also, then these bound improves, basically the probability of making a generalization error goes down, and then it has dependence on epsilon as well, and then and the size of the bad hypothesis class. So this will be the end of today's lecture, and we will continue with this in the next class. I will write down the final result on this in the next class. So thanks a lot.